Alright, so this video is going to show you the second part of the scenario 1 and 2 analysis where we actually analyze the forces exerted in the x and y direction of the tilted axis. So a couple lines of reasoning we're going to have to go through here first to actually analyze this force diagram along the tilted axis, along the incline and perpendicular to the incline. First, if this is theta down here, we want to analyze the vector components for the force of the earth. If I draw in those parts, those perpendicular parts, we're going to find out that part of the force of the earth is parallel to the y-axis and part is parallel to the x-axis. So we need to find out what this angle is in there. Now if I look at theta, let's just imagine for a second that this is 30 degrees. The earth drops straight down, which is perpendicular to the horizontal line here, which makes this 90. So in here would then be 60 degrees because there is 180 degrees in a right triangle, and this is 90, this is 30, that would be 60. Which means if you look at this dotted x-axis and this dotted y-axis, those two axes are perpendicular to each other. So 90 minus 60 would make this 30, or your original theta. So when we come over here to this diagram, we can draw in our theta as that angle right there. Alright, so before we write out Newton's second law in the x and y direction, I'm going to draw in the components over here so we can see this a little bit easier. Alright, so along the y-axis and parallel to the x-axis, mg would be the magnitude of the earth pulling down. So along the component along the x-axis, if this is my hypotenuse, this is my right triangle, this is going to be opposite of that. So this will be sine of theta is equal to the x component divided by mg. Or if we multiply through by mg, this will be mg sine of theta. Now if we look along the y direction, mg again is our hypotenuse. This is our adjacent sine. So cosine of theta will equal the y component divided by mg. If I multiply through by mg on both sides, we get mg cosine of theta. Alright, so we're going to look at the sum of the forces in the x direction divided by the mass will equal our acceleration. Alright, looking in the x direction, we know our acceleration is pointing down the incline. So I'm going to call this positive. Down the incline is the direction of my acceleration. So A will equal. Now, I have to look at my arrows, and if I look here, my friction is pointing up the incline, which in this case I'm making negative, and down the incline is positive. So friction will be pointing up the incline, and mg sine of theta, if you look at this, it is parallel to the incline. So it will be mg sine, got it in there, of theta minus your frictional force. Now remember, friction is mu times the normal force. So instead of writing F of the surface on the object, I'm going to put in mu times the normal force. Divide all of this by m. Now we have Newton's second law set up in the x direction. So in the y direction, all right, again, if we look at our acceleration, if a box is sliding down an inclined plane, it's accelerating parallel to the incline, which means perpendicular to the incline, the acceleration in the y direction is going to be 0. So we're going to write 0 is equal to, and if we look at this, the normal force is exerted perpendicular to the incline along the y-axis. So the normal force minus, and mg cosine theta, I don't know where that cosine disappeared to, but that should be mg cosine theta, is going to be in the x direction. So this is going to be mg cosine of theta. Now, wondering about this a quick second, remember that cosine theta would equal the force of the earth in the y direction divided by mg. So if you multiply through by mg, you get mg cosine theta. I'm not quite sure where the green writing disappeared to, but it disappeared to at some point in time. So anyways, back down to here, you now have everything set up in variable form for the horizontal direction and the vertical direction. Now, if you need to figure out the normal force, you can add mg cosine theta to both sides, and you have the normal force is equal to mg cosine of theta. Okay? This then can be substituted in on the other side of the equation if need be. So you have mg sine of theta minus mu times mg cosine of theta, all divided by m. Now, if you notice very carefully, you have m's in both terms, and you're divided by an m, so those could cancel out if you're not given a mass. So don't be surprised if you don't have the mass of an object, you can still solve for the answer, because the m's sometimes divide out. All right, so this is how we set up to this. The next couple videos will be of some example problems.